We're going to talk now about ZFS, which is a file system developed in the early 2000s at Sun, now part of Oracle. It is available for Linux, BSD, unfortunately not directly available on the Mac. Let's look first actually at a little bit of history. So historically what we have had is a single file system on top of a single drive. So we might have, for instance, well, gosh, 1 gigabyte's a little small these days. Let's make it a 100 gigabyte hard drive. And that changed along the way. So eventually what happened is we added volume managers. So volume managers go ahead and provide a, let me show you in a diagram. So for a volume, we might have a 200 gigabyte volume, and that's broken down . So we've got a 200 gigabyte volume, which is basically managing two 100 gigabyte disks. And we've got a file system on top of that. So the volume is providing a block interface. So basically it looks like a single hard drive, except it has 200 gigabytes worth of blocks rather than 100 gigabytes worth of blocks. All right, so what are some of the problems of this? Well, some of the problems of this are that it is hard to extend the size of a file system. It's hard to share disk space among different file systems. So here's what ZFS does. ZFS says instead of having this situation where they've got file systems either using a drive or multiple drives, or another possibility is you could certainly have file system 1 and file system 2 sharing a single drive. The problem is how you have to arrange this is one file system gets one part of the drive and another file system gets another part of the drive. And it's very hard to change that after the fact. All right. This comes up, for example, let's say you have a Mac and you want to reserve a Windows file system on it because you're going to be running boot camp. You have to specify ahead of time fixed what those relative sizes are going to be, and then it's very hard to change that afterwards. So the ZFS approach is different. The ZFS says basically we're going to have a storage pool. And this storage pool can handle drives. Some of my drives are prettier than other drives, but something like this, all right? And it can actually also handle, if you want, mirroring. So this signifies that these two drives are the same size and are actually kept up as copies of one another. And we can do the same thing for here and the same thing for here. Or we could specify we want 3 copies. Or we could specify some more RAID type approaches where we have, let's say, 5 drives, 4 of them are going to be used for separate copies and 1 is going to be used to provide some error correction. We're not going to get too much into that error correction discussion these days. Now, what happens on top of this storage pool? On top of this storage pool, we can create a file system. And we can create multiple file systems. And the size of these file systems are not determined ahead of time. So they can shrink and grow as needed. And all that really matters is the total amount of disk space is enough to satisfy all these file systems. You want more disk space? Add more disks to the storage pool. You've got a disk that goes bad, like let's say this one here. Go ahead and remove this disk, replace it, and then this single copy will copy over to this multiple copy. So part of what ZFS provides is this decoupling from file systems to drives. And instead, we've got this intermediate virtualizing layer. It's not unlike the idea of a virtual memory. And you can think of this as, instead of having applications having to go into some physical memory, we're actually going to some virtual memory that gets allocated to particular drives without the not underlying file systems, without the file systems caring about it. So the file systems are actually not referring directly to anything on a particular hard drive. They're referring to some indirect value that the storage pool manages. And that way it can go ahead and reallocate blocks as it sees fit. So you might have a block in the ZFS that originally starts on this drive, but might migrate to a different drive over time. So we've got our file systems that are of dynamic size. All of the storage in the storage pool is shared among each file system. And the pool size itself can be expanded, so you can easily add drives. In addition, what ZFS provides is, so part of what it provides is future proofing. Okay, we don't have maximum size, or so we do have maximum sizes, but they're very, very large. So it uses 128-bit addresses rather than 32-bit or 64-bit. So those are large enough to address an awful lot of storage, more than you'll ever need. The size of these file systems is very large. You can have lots of file systems and so on. In addition, what does it provide? It provides checksumming. So this is a very nice way of ensuring that your data is safe and doesn't get corrupted, or at least really that we know about corruption. We'll talk about that in more detail. We have copy on write. You'll remember that in the case of both ext3 and xv6, the solution we used for being able to do transactions was to have a journal. And that journal required some sort of recovery. That is, the main part of the file system, or the totality of the file system and the journal, meant that you had to apply the journal to the file system to get to its current value if any crash happened. The way ZFS works, if a crash happens, that is if your machine goes down, the status of all of the data is such that it is all correct. You might say, how the heck can that happen? And the way that basically works is through a fancy copy on write system that we're going to talk about. And that really gives us our transactional. So we can easily do a variety of changes to a file system and commit those as one transaction. We can actually do a variety of changes actually across file systems if we want, and those all get done actually in one transaction. So let's say we are concerned about the fidelity of our data, and let's look at one way we can do that. Okay, so let's say we decide that we have a data block. So we have a data block, and we are going to reserve some space and add a checksum. What are we saving? All right. And we obviously usually have some sort of a pointer to that data block. Often it's an inode or something else, but often we have some sort of attributes, and then we have a pointer. By pointer, what I mean is we normally have some sort of a block number. What does this checksum protect against? It protects against bit rot. Right, so bit rot is basically where, the magnetic media becomes weak. We have some sort of a bit change in front of that. We have a bit change in this data block or in the checksum. So we can see, oh, this data block is not correct. So that's a good thing to be able to guard against. Does this guard against phantom writes? No. First off, what the heck is a phantom write? The phantom write is when you tell a disk drive, hey, I want to write to block 53, it just doesn't write at all. Why does that not work? Well, so let's say we have this, let's say it's an inode, and we have a block, and we go and we update the block. And so we say we calculate the new checksum, and we write the block, and it goes and writes it. And then we come back and reread. Well, if the block was never written at all, we're going to get the old block with the old checksum, and the checksum is going to match. So as far as we're concerned, we wrote a checksummed block, and then when we read back, the block still checksums, but unfortunately, it's not what we just wrote. So the phantom write is it doesn't really happen. That's to be distinguished from a misdirected write. You try and write to 53 and it actually writes somewhere else. Or you try and read from 53 and it actually reads from somewhere else. Again, we have the problem that if we happen to read a block whose checksum is self-consistent, that doesn't really tell us that it's ours or that it's the latest version. Other things it doesn't protect against would be, let's say, memory errors. And these are real things. That is, cosmic rays are one way we can actually get a bit change in a memory location. So we went ahead and we read in our data into our block, yet one of the bits got changed once it was there. No, we don't have any check against that. What else do we not have checks against? Driver bugs. If we're writing, so the disk is acting correctly, we're actually telling it the wrong thing to do. Accidental overwrite. So I distinguish this from a driver bug because this is actually maybe a user error. So the user accidentally did something. So all that this internal checksum protects against, what is this case here? The bit rot. Let's look at an alternative. So the alternative is this. We are going to store in our disk block just our data. Okay, so this would be our disk block. Here's another disk block. Rather than having an internal checksum, we're going to have an external checksum. Let's say, for example, that these are referenced from inodes. Okay, so this, let's say the first one is referred to from this inode, and the second one is referred to from this inode. And we are going to put a checksum at the location of the reference, external to the block itself. So what does that mean? Well, that means that when we write this disk block, we're going to also write an associated checksum here. If this disk block didn't actually get written, later on when we read it, we're going to look and we're going to say, I'm going to go checksum it now, and it doesn't match this checksum because I have the newest checksum, but this might be an old data block, or it might be an incorrect data block. Right? I might have gotten the wrong data block, or I might have gotten some noise as I was reading back. That's a case, again, where bit rot kind of and cable issues, right? What if you have a bad cable that's giving some bad values? So this will deal with the accidental overwrite. So if someone accidentally overwrited this block, we'll be able to find out. If we have a phantom write, that we did this write, or we thought we did the write, but it didn't actually happen, we'll know that. A misdirected reader write. So if we asked to write this block and I wrote it somewhere else, then when we read it back, we'll find out. Misdirected read. We asked to read this block and it returned a different block. It doesn't matter if its checksum is, its internal checksum weren't consistent, it's not going to match this checksum. Memory errors, driver bugs, all these, this will catch. And then we go a step further and we say, well, this is a block, let's say, of inodes. There's some reference to that. Right? So we have some sort of, attributes or something, and then a reference to this block. How are we going to ensure that this block is correct? We're going to go ahead and put a checksum. So anytime we have a block of data, we are going to have some reference to it, and it's there that we're going to put a checksum. This is the idea of this, and we can keep doing this all the way until we get to some root and just store, as long as that block is safe, we can guarantee every other block is safe through this consistency of going down, basically saying, well, whoever pointed to this block has guaranteed that this block is correct, including the checksum. Now we can use this checksum to verify this block. We can use these checksums to verify this block all the way down. This is called a Merkle tree. So in Git, we're using hashes, and the Git hash basically hashes together the changes that have made in this commit along then with the block of the previous commit. And we can move that all the way back in history. Another use of the Merkle tree is in Bitcoin. Right? So in Bitcoin, this is how we can basically have a hash of the current transaction and the past block. And then this is the blockchain. And then the previous blockchain has a hash of the transactions that have occurred plus the previous block, and so on. And we just keep working our way back. So this checksum allows us to have end-to-end reliability. There is a saying in computer science that the fundamental theorem is all problems can be solved with an additional layer of indirection. There's an associated, I think, theorem of optimization, which says that all programs speed can be improved by removing a layer of indirection. And those two certainly are in some conflict. So we've seen that level of indirection with virtual memory, right, where we have a virtual address, and that maps via some mapping to a physical address. And that provides us a large amount of flexibility. We're going to use that same flexibility with ZFS. So ZFS is broken down into various levels. We have our device driver. And when we look at the device driver, it has some sort of a addressing that's kind of looking like physical device and offset. Or you can think of it as physical device and block number. On top of that, we have the storage pool allocator. So the storage pool allocator communicates with the device driver in terms of physical devices and offsets. But what it provides up above is a different abstraction. So it provides a device virtual address. So the storage pool allocator contains a mapping internally that says basically this device virtual address maps to what particular physical device and offset at this point in time. Right? If it chooses to change its location, it can just update the mapping. But from the point of view of anything higher, the device virtual address is all that it's seen. On top of that, we've then got a data management unit. So the data management unit is providing, on top of this, some triplets, really, of data set, and then an object within that data set, and then an offset. So if we can think of it, what the data management unit is doing is providing an abstraction of data sets, and then within data sets, we are providing objects of various sizes. The storage pool allocator, by the way, its interface is an interface that's similar to malloc. So you can allocate and free. And the objects you can allocate and free are of some varying sizes. All right. We wouldn't allocate or free a gigabyte object. We could certainly allocate a 4K object or a 1K object or I believe a 16K object. Okay, so there's some various sizes that you can do, but you allocate those and free those. So the storage pool allocator actually knows which of these are in use and which are free. That is, which of the device virtual addresses are in use and free. And from then on, it can determine when something is free, that can be free down in the device driver. The data set, the data management unit is providing this higher level interface, and these can be large. How are they implemented? Well, they're implemented with direct and indirect blocks. So it is similar to an inode in the sense that when you've got a data object, it has a dnode, and this can have direct and indirect allocations from the storage pool. I'm going to call them blocks from the storage pool allocator. Right, this is the storage pool allocator, and this is the data management unit. So if I want to create a 1 megabyte object here, I'm going to go ahead and have a dnode and have the dnode have some direct blocks and then some indirect blocks. So we'll have a sequence of different allocations from this storage pool allocator. As an example, right, let's say this is the dnode, and it might have direct blocks, and then also, let's say it might have an indirect block. So this is very similar to the inode concept on Unix. What are these objects used for? Well, these objects are actually used to implement file systems. So a dnode could represent, I'm going to not say B, right, because a dnode is just basically storage for an object, but it could represent. And I'm going to really, it's not the dnode that's representing, I'm going to say it's one of these objects that is implemented with a dnode. An object could represent a file, a directory, a symbolic link, and so on. And then there can be references between those. So I can have a directory dnode whose contents, let's say, is this block, and whose value might be very similar to what you're used to, a dot and a dot dot and a foo, and then these would all be dnode numbers. How are the dnodes represented? Well, one of these objects is the dnodes. Dnodes themselves are fixed size, just like inodes are fixed size. So we've got this broken up into basically an array of objects. So each object here is represented by a dnode. The dnode contains both direct and indirect references to blocks retrieved from the storage pool allocator. Those blocks are virtual addresses, so where they are on the actual disk, we don't know, and it could be different at different times. The storage allocator is going to take care of that. Above this level here, we have a POSIX level. POSIX is just the standard for Unix type systems. So the POSIX level is going ahead and interacting in terms of file system operations. Right, so like link, unlink, open, etc. So if we are trying to look at an open, that looks like it's opening /user include /standard.io.h, it might go ahead and get the data set for the particular file system. So this is going to use this data set to represent a file system and another data set to represent another file system. So it's going to use that. And then it's going to use the slash object that somehow it'll find in there. And then it'll go get the object and then read the data to find the directory entry for user. And then that'll give it a dnode number, right? And it can then go get the object with that object. So this is the dnode number, and it can basically be traversing down the directory hierarchy until it actually gets to standard.io.h, in which case it can go ahead and obtain the its dnode number and then put that in its open file table. So let's look at the idea of copy on write and see how that helps with all this. So let's look at copy on write. We'll look at conceptually for a moment, and then we'll talk about how we're actually doing this with respect to ZFS. So let's say we have an initial block tree. So we have got, this is our Uber block. And it doesn't have an external checksum. Its checksum is located within itself. It's going to point to some, let's say, block, and this is a simple block tree that's just binary. Okay, so here we've got our block tree. These are our actual blocks, and notice it's not a necessity to be the same size. Also, remember, we're going to have checksums here. So these are going to checksum. This one, for instance, is going to checksum this block. This is going to checksum this block, and so on. This is going to checksum this block, okay? Which in turn has checksums for this block. So this checksum actually validates the entire subtree. This checksum validates this subtree. And this checksum validates this block. And then we have an Uber checksum here that validates the block itself. All right. So what's going to happen if we need to change a block? Hell, while we're at it, we'll change a couple blocks, okay? So let's say we change 2 blocks. We want to change these 2 blocks. If we change these 2 blocks, that's going to also force us to change this block because the checksums will change. If we change this block, that's going to force us to change this block, and that's going to force us to change this block. So changing these 2 blocks also forces us to change any parents of those blocks until we get up to the root. Fine. How are we going to do that? We are not going to actually change them. Instead, we're going to do a copy on write. Let's look at that. So we are going to leave this one alone, and we're going to create a new block. The old one stays there, stays on disk. And this is the other one we want to change. We're going to create a new block. Well, we just said if we change these blocks, checksum's going to change. We're going to need to change the parent block. We're not going to change the parent block. We are going to make a duplicate. We're going to make a duplicate, and we're going to update the checksums. So this is now checksum prime in some way. And this is checksum prime prime. And we have pointers now. Have we changed anything yet? No. As long as we get to everything from the Uber block, we have changed nothing at this point. We've just created 3 new blocks that happen to share some parallelism with the existing blocks. But if we follow down here these old references, we haven't changed anything. Now what do we do again? We make a copy of this block. We don't need to change this block here, so we can point directly to it. We also don't need to change the checksum because it's just fine. So that's a check, just like it was. This one is going to be a check prime prime. Okay? It's different. Finally, we're going to make a duplicate of the Uber block. It's going to point down to the new child block. It'll have a new checksum here. Since we've changed this checksum, the checksum of the block itself is going to change. And all that we really have to do to atomically affect a transaction where we changed both these blocks is one change. We need to change which is the Uber block. Change it from here to here. That one change changes our look of the entire set of blocks. These blocks happen to stay the same. These blocks change in one fell swoop. That is how we get our atomicity. What's more, we also get checkpointing for free, right? If you can imagine, this was a change that happened in the last 5 seconds. So we had some system calls that were doing some file system changes, and these are the changes that happened. We changed this block and this block. This really could be much bigger, right? We could have changed a bunch of blocks, but those blocks will filter up. Some of the internal nodes won't change. Some of the internal nodes will change. We get up to the top, we make one change, and now we can easily see what was the state of the file system 5 seconds ago versus now. If I wanted to snapshot this one, I could just keep a reference to this Uber block and have it forever, possibly. I could just name this, my snapshot as of today at this time, and just keep that around. And then keep moving the current Uber block as it changes 5 seconds by 5 seconds by 5 seconds, assuming that's how often we're updating the file system. And in fact, it's quicker to have done this snapshot and not bothered freeing out these unused blocks, because we didn't need to do anything. We don't even need to tell the storage manager to not use those. We're actually going to have a big array of Uber blocks, like a circular log that we can use of Uber blocks, and just keep track of which the highest one is. Some of them we might want to also save for posterity. And at any point in time then, we can go ahead and reclaim pages that aren't referenced from any Uber block. Right? Once the Uber blocks are finally, let's say, age out and aren't used anymore, right? Because we will have a whole sequence of these. At some point, we're going to say we don't want them anymore. Like if it's in this circular log, as we come back, we don't need them anymore. And then any of those that are gone, any of the references we had to them, we can go ahead and garbage collect those. We can garbage collect these, what are objects, and that will in turn then call free to the storage system. This is conceptual. Just because we have a hierarchy doesn't mean we are talking about the directory structure. This is not our file system directory structure. This is not equivalent to /user, /include, and so on down there. So if you make a change to a file that is nested deeply in the directory hierarchy, we are not going to have to make any changes to the parent directories. Okay? Don't think of these as the directory structure. We'll talk about what it is actually in a moment. So let's look at, we have in our object set, right, this is sort of the one layer, we have our object set, which is all of our denodes, and this contains directories, files, let's just say we'll ignore symbolic links and other things. Let's just say it's files and directories. Right? And let's say there's one particular file that we are going to want to change the contents of. We're going to want to do a write, perhaps to append. Right? So we are going to go ahead and append some data to this. The way that is actually going to be implemented, right? We are going to be modifying its dnode and adding perhaps an indirect block, certainly a data block. Okay, so we're going to add a data block. This data block is actually, right, something we get from the storage layer. We are going to have to update the indirect block, or possibly blocks, if it's multiple indirect blocks, that refers to this. Okay. So let's say there's an indirect block here. The indirect block, the checksum of that is now going to change. So that's going to require any parent indirect blocks to change all the way up to the dnode, right, which is going to change. The dnode's checksum is going to change because the contents of the indirect block has changed. Now the checksum of this object set has changed. This is referred to from a file system object. Okay? This file system object is referred to from a different object set. This is the meta object set layer. And this is referred to from the Uber block. So the object set has a lot of sort of contents in it, right? The contents in it includes multiple file systems. So every file system just contains a reference to an object set. We have snapshots. So this is the idea of I want to capture the contents of my file system at a particular point in time. Okay. There are clones. The only difference in ZFS is a snapshot is read-only, and a clone actually says, I want to, it's like a fork. Okay, I'm going to change what happens. So these are all different objects referred to by dnodes from this object set. So when you change a file, let's say you add a data block, it's going to be a new data block, of course, that will get allocated from the storage subsystem. Then we're going to have to update the indirect block that refers to it to add its new block number. Or that is, it's really not a block number, right? It's an actual virtual address. So that's going to be a data virtual address. And then we're going to go ahead and update the dnode because the checksum of the indirect block has changed. When we update the dnode that's in the object set, that's going to cause us to update the checksum here. That is going to cause us, since that's really located in here, that's going to update the checksum of this, which is going to update the checksum of the uber block, and we now have a new uber block. So when we change the uber block, that's going to change the file system, that's going to change the dnode, that's going to change the indirect block, that's going to change the data block here. And having a snapshot is just a matter of pointing to an old version of an object set. A clone is the same sort of thing. One of the things I want to point out here is we've changed a file. We don't have to change anything about the directory that that file is in. Okay, because if we look like it, let's say this is the directory entry for the file is referenced from this object, which is a dnode index. And the dnode index of the file hasn't changed, so there's no need to change that. If we're creating a new file and writing to it, then yes, of course, the directory is going to change. So that's going to change the directory entry, basically. So the contents of the directory will change. If we then write to that file, of course, that's going to also change the user data. We can have any number of modifications that we want to the file system. We can make as many as we want, and they'll be in a single transaction, because what will happen is they will all get new rights to the storage system. And that's a key point here. When I say update the indirect block, this is all copy on write. So copy on write, copy on write, copy on write, copy on write, all the way up. So the height of this is independent of the directory hierarchy. The height of this is going to be more dependent on how many indirect blocks there are. If we didn't have indirect blocks, then it's about 4 or 5 entry size. So this can be very quick. The other thing about this, and the reason it can be very quick, is imagine where we're writing to the storage system, right? The storage system, we are just saying, give me, do a disk allocation, do a disk allocation, a storage allocation, a storage allocation, a storage allocation, and then finally a special place for the uber blocks. Those storage allocations and your writes, equivalent writes, could be done contiguously on disk. So the storage system can choose where to put those and can write those contiguously and very fast, just as we were saying when we were doing the journaling. So let's look at what happens in terms of I/O. So let's say we've got some system calls. Those, the ZFS POSIX layer, are going to turn into changes to particular objects. So you might have a number of different system calls. Some of them might be modifying directories, might be modifying files. And so those are going to turn into something along the lines of, like that. And then the data management unit is going to bundle transactions into transaction groups. So what we can actually do is take a system call, and a system call will turn into a transaction, feed that to the DMU. Take another system call, that's a transaction, feed it, and so on. And those will all turn into transaction groups that'll all get transacted together. So these will flush. When what happens? Well, either our memory is full because we've got these all in memory. So And so that may be some percentage of system memory we're using, or I should really say, at a regular interval. What's that interval? I don't know, 5 seconds, 10 seconds, 15 seconds, something like that. That's fine. And then what happens? Then, right, think of the DMU. The DMU is going ahead and making writes to disk virtual addresses. So those still eventually, the storage pool allocator, are going to go ahead and send those to physical media. That is, actually make calls to the drives. So it's going to send up the blocks in the transaction group and send those blocks that were sent from the DMU to the physical media. So that's how the writing happens. There's a lot of caching that happens, and a lot also of and there's also a lot of prefetching. If there's a block that's not cached, then there's a prioritized I/O with higher priority than the pending writes. So the reads have higher priority in the writes. And then there's also sort of an adaptive cache that tracks the recently used blocks in memory. So the copy on write, we already talked about that the copy on write means that we are turning random writes and making those sequential, because we're never modifying a block that's there. We're always writing to new information because it's always a copy on write. We do have dynamic striping. So striping basically says something like this. Let's say we have these 4 hard drives and we want to write 4 blocks of data. Rather than writing all 4 blocks of data on one drive, we're going to spread it out and do 1 here, 2 here, 3 here, and 4 here. The key thing is it's dynamic. And so if we in the future add another drive, then we're going to stripe across all 5. That helps with eliminating hotspots, so we're not just hitting one drive all the time. Okay, so we're doing 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. If we've got 8 blocks to write. If now we add another drive, then if we have 8 blocks to write, we'll write 1, 2, 3, 4, 5, 6, 7, 8. So this is different from the static striping where you're going to say, I know I have 4 drives and I'm going to always say that for a given file, let's say the blocks are going to be laid out, boom, 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 or not let's say not even a given file. Let's say that the block numbers are going to be laid out 1, 2, 3, 4, 5, 6, 7, 8, and so on. And then there is also, let us say, we haven't even talked about some of the use of the checksums. So let's say we have a drive and we have a mirror. So this is a drive and this one is its mirror. That means when we write, we're going to write to both drives. Does that slow anything down? Shouldn't, right? Because we're just writing to both. What will happen though is when we do a read, we can read from either one, right? Whichever one is available. So let's say we read a block from here, okay? We read a block and then we can use the fact of the checksum to see that actually this block is not good. So therefore, we should go ahead and read from the mirror. Not only that, once we've read from the mirror, we should write back to the original drive with the correct data. Let's say drive goes bad, and we now have to replace it. Okay, so we've now got, this drive's bad, we've got a new one. Well, this drive doesn't have any of this stuff on the mirror to begin with, right? So we've got to copy from the mirror to the new drive. Do we have to copy everything? No. We only have to copy the blocks in use. So that's what we call an intelligent resilvering. Resilvering is an idea of taking a mirror that is bad, right, where the silver on the back of the mirror has been lost in some ways and putting new silver on it. So that's the idea here. We have a mirror, this original drive, and we want to re-put the new silver on, that is, recopy the blocks from mirror to new, mirror to new, and mirror to new. But the fact is, ZFS knows exactly what blocks are in use and not use. So it doesn't have to just copy the entire drive, which could be quite slow. It can just copy the disk's blocks that are in use. That is ZFS. Some of the important things that we see about ZFS are it's extremely expandable. So it can take basically think of it as an unlimited number of disk drives and disk sizes. File systems are extremely easy to create. Because of the copy on write situation, we never have a situation where the disk is in an uncommitted state. Right? We're always either seeing the state of it before we've done a transaction group or after we've done a transaction group, because the commit point is really writing that Uber block. The external checksums allow a lot of safety, and so you can see not only when things have gone bad, but more importantly, if we use mirroring or parity drives or anything like that, allow a chance to actually fix them. A last thing you can do is actually, let's say you've got two drives, let's say they're a mirror, but it could be any sort of a parity system. It's possible some of these blocks are just silently going bad, right? And so what you can do is actually run a scrub operation that just goes through and reads all of the blocks on a drive and just verifies, looking at their externals, that the checksums are valid. And if they're not, then go ahead and copy them over from the associated mirror.